Greetings. My name is Bill Skamrock, and in this presentation we're going to review the spatial discretization of the MPAS-Atmosphere dynamical core. We're going to begin by looking at the vertical grid, then we'll look at the horizontal mesh, which here is depicted on the sphere. And as you can see, it uses spherical centroidal Voronoi cells, nominally hexagons, but there are also some pentagons and seven-sided cells on this mesh. We'll look at a few terms that show up in the dry dynamics that illustrate how the differencing is performed. We'll look at a few nameless parameters that are associated with the dry dynamics, and then there'll be a few references if you're interested for more details on how the MPAS-Atmosphere dynamical core is constructed. There's a second lecture that's associated with the spatial discretization, and that deals with the transport operators, both the resolved part of the transport, nominally what people call the transport scheme, and also the dissipation parameterizations that are all cast in forms of a turbulent transport. So that's the other lecture you may want to consider looking at if you want to understand in more detail how the MPAS dynamical core is constructed. We'll begin by looking at the vertical coordinate in the MPAS atmosphere. Vertical coordinate that we use is a generalized height coordinate, which means that down low, for example, along the surface, the vertical coordinate follows the terrain. It is coincident with the terrain. And as you go up in the atmosphere, it ultimately relaxes to a constant height coordinate, meaning that the height of a coordinate surface is constant in terms of the vertical geometric height z after a certain amount of time. It's generalized also in that relaxation to a constant height coordinate high up is done by using the terrain at the bottom, but filtering that terrain as one goes up in the atmosphere to remove the fine scale structure before you remove the large scale structure in terms of that relaxation. And that'll be shown in a minute in a couple slides here. So the height coordinate. This is the equation for the height coordinate here, that the height z is equal to the coordinate we use in MPAS, which we denote as zeta, plus some function a, which is a function of zeta, times the surface height, which you can see we've written not only as in the horizontal, x and y, but also in the coordinate zeta. Now this is where we control how the terrain influences the coordinate. If you look further down on the left-hand side here, that function hs, which is the surface height, which is now defined on the full three-dimensional mesh, we smooth that height field as you go up, as the coordinate zeta increases, so that the small scales in the height coordinate are removed gradually as one goes aloft. And here's an example on the right of what that smoothing does in this generalized vertical coordinate. If we look at the basic terrain following coordinate, which just linearly relaxes to a constant height at the model top, where the model lid is, you can see that down low here, looking through about 5 kilometers, you've got all the structure in the surface elevation that's reflected on those coordinate surfaces, those horizontal coordinate surfaces. Whereas with the smooth, generalized height coordinate, you can see that there's still some large-scale structure when you get about midway up in the atmosphere here, at about 2.5, 3 kilometers, but a lot of the small-scale structure is removed. That's the generalization that we've introduced in this height coordinate. So this is what MPAS uses, and the default is to relax to pretty much almost constant height coordinate by about 15 kilometers in typical MPAS-A realizations and what we use for our defaults. And that's what you'll find when you run tests, for example, using MPAS-A out of the box, that kind of height coordinate. Here's an example of a cross-section through the Andes. Mount Everest is the mountain, the tallest peak that's on the left side of the domain here in this west to east cross-section through the Andes. And on top, we're looking at our typical formulation for our smooth terrain following coordinate. And you can see the small-scale structure goes away as one goes aloft. As you go to finer horizontal meshes, plotted at the same scale, you'll see more small-scale structure as you go aloft on those finer grids, but those finer grids are better able to resolve those small-scale structures in the topography. So that's is how it should be. But you can see that by the time you get up to here, almost 17 kilometers, that almost all the structure in the terrain is removed from the coordinate surfaces. Down below is that basic terrain following coordinate, and you can see the structure in the terrain extends well up into the atmosphere here. The model top on this mesh is up at 30 kilometers, so you can see it takes a long time for that structure in the terrain to be removed from the coordinates. And the thing to understand here is that the error in the horizontal discretization will have a component that's related to the non-smoothness of this terrain, the higher order derivatives in the horizontal surfaces in terms of how the height varies along those horizontal surfaces in the model. So these smooth coordinates result in more accurate solutions, and that's why we have implemented them in the MPAS-A model. Looking at the horizontal mesh, we call it a mesh as opposed to a grid because there's no global coordinate here. This is a truly unstructured mesh. To know where your neighbors are, you just don't increment in a coordinate direction because there's no global coordinate to follow. So MPAS uses a spherical centroidal Voronoi mesh, and that's depicted here on the left. In these meshes, they're mostly hexagons, meaning six-sided cells, but there are also some five-sided cells and some seven-sided cells. So we have quite a collection of different cell shapes and sizes here. Typically, though, the number of pentagons and seven-sided cells are much, much less than the number of hexagons. So, for example, in a traditional mesh, uniform mesh, that would be the icosahedral mesh. And that typically has 12 pentagons and all the other cells are hexagons. On the 1 degree mesh, for example, there are 40,962 cells. Of those, 12 are pentagons. The rest are hexagons. We use a C-grid discretization on this spherical centroidal Voronoi mesh, which means that the velocities are defined as the normal velocities on the cell edges here. In the spherical centroidal Voronoi mesh, the cell edges bisect the lines connecting the cell centers. Here from A to B, the cell edge AF bisects that line, meaning it intersects that AB line at the midpoint, and it's perpendicular to that line. So you can see right away that that velocity, the normal velocity to that cell edge, is going to point in the same direction. It's going to be tangent to that line along connecting cell centers A and B. Likewise for all the other edges. So that's the aspect of the centroidal Voronoi mesh that we take advantage of. We also take advantage of the fact that the cell center is the center of mass of the cell. That means that this is the center of mass of this particular cell. For B is the center of mass for this cell, and likewise for the other cells. There are methods for generating meshes given a density function which prescribes how fine or coarse one wants to mesh in a region of the area that you're trying to generate the mesh for, in this case, the sphere. The mesh that's depicted here on the right has high resolution in the equatorial region going away from the equator and lower resolution at the poles. So as you can see, if you look closely at the farthest right part of the mesh, which is a zoom of this global mesh you see, you can see that the cells vary in size, that the variation is smooth going from fine to coarse. And that's something we like about the MPAS model. That smooth variation of the mesh removes or minimizes the error in discretization in the region where the mesh is varying. When you discretize the equations to solve them, part of the error in that discretization is going to be related to how fast the mesh is varying. And here we can choose to generate our mesh such that it varies slowly. This one, as you can see, some of the cells are kind of odd shaped, but this is just a preliminary mesh which we refine further as part of our process to generate these meshes. So ultimately, the mesh cells vary smoothly across this mesh, across the transition regions. Typically, the cell sizes or the distances separating the cell centers doesn't vary by more than a few percent as you're traversing from a fine region in the mesh to a coarse region. There are two sets of terms in the equations that I would like to explain how they're discretized. The first set of terms are gradient operators. If we look at the horizontal momentum equation depicted here, there are two horizontal gradients. There's the pressure gradient, and also because we've cast these equations in terms of a vector-invariant set, the transport terms in the momentum equation have been transformed into a term. One of the terms is this gradient of kinetic energy. That's what K stands for here. This is kinetic energy. And also a more generalized, what we call a nonlinear Coriolis term, because instead of just a Coriolis parameter here, F, we now have eta, which is the full vertical vorticity, F plus the relative vorticity. So that's what the vector-invariant equation set means, that you've transported the nonlinear transport terms in them into this formulation here. We have made no approximations in these continuous equations. When we go to the finite volume formulation that's used in MPAS, we now have to discretize these terms. So that's what we're going to look at next. So first, for the gradient operators, what we have here is two cells, which cell centers at P1 and at point P2. These are nominally pressures for looking at this pressure gradient here. And because of the property of the Voronoi mesh, the centroidal Voronoi mesh, these are located at cell centers, but perhaps more importantly, this velocity is tangent to the line connecting the two pressures. So the pressure gradient along that line, which is what this operator is, it's looking at the pressure gradient along this line, is just easily discretized as the pressure at point 2 minus the pressure at point 1 divided by the distance between the cell-centered points. And remember that the cell edge bisects this line, so it is a full second-order accurate approximation to the pressure gradient. So we're taking advantage of how this grid is constructed. This is the same way that the grids on regular grids, which have rectangular meshes, this is the same operator they use because they've got a global coordinate and the velocity is tangent to one direction in that global coordinate, and typically the pressures and densities, etc., are located at the cell centers, and they have the same property. But now, in this much more general mesh, we also have the same property for the C-grid discretization in the horizontal momentum equation. Now, that C-grid discretization means we're solving for this normal velocity at this cell phase. So that's what we're doing in this C-grid approach. For the vector-invariant formulation, we also need to take the derivative of the kinetic energy in the direction of the velocity at the cell faces. And first thing is, we don't have the kinetic energy. It's not a prognostic variable, so we have to compute it. The equation On the left, in the blue box, is an equation for how we compute the kinetic energy that's valid at the cell centers. So we're going to define a kinetic energy at the cell centers just like we define the pressure at the cell centers, and we're going to take its gradient in the same way. So the question here is, how do we compute the kinetic energy? The equation determining the kinetic energy at the cell centers is given in the blue box on the left. That kinetic energy at the cell center, which is circled in red in the equation and is circled in red in this depiction of the MPAS mesh, that kinetic energy is the sum of two terms. The first term is the weighted sum of the square of the velocities on the cell edges that are part of that cell. So for a hexagon, there are 6 edges, and you square the velocity, that's the predicted velocity on that edge, and you sum them. The weight here, WEI, is a quarter, but we're going to take a weighted sum, so that's going to be one part of the kinetic energy at the cell center. The second part is a term associated with the kinetic energy evaluated at the vertices. The kinetic energy at the vertices is a weighted sum of the square of the velocities on the edges that come together to make that vertex. For example, if we look at the vertex here, where this larger green circle is, that's one of the vertices here. The kinetic energy at that vertex is the weighted sum of the square of the velocities at these 3 points, at the edges that make up that vertex, those velocities, and the weights here are half. So that's the kinetic energy of the vertex. In terms of their weighted average, those two, we use beta equals 3/8. So we're taking 5/8 of the kinetic energy computed at using just the cell edges that are part of the cell, and then we're using 3/8 the value of that kinetic energy estimate at the vertices. We're motivated to take that weighted average because we determined in early testing of the MPAS-Atmosphere dynamical core that just using the velocities at the cell faces that are owned by the cell, that make up the cell, essentially setting beta equals to 0, in standard test cases for atmospheric cores, in this case a baroclinic wave test case, this is Jablinowski and Williamson baroclinic wave, very well known, it produced noise in the vorticity field. Now this is without any dissipation at all, so this is just about a day before the front collapse and you need dissipation. But when we saw this structure, we realized that there was a problem there. And it turns out that by taking the weighted average of the kinetic energy and using now the kinetic energy defined at the vertices as part of that averaging process with beta equals 3/8, that noise is largely ameliorated here, as shown in this bottom plot where we use beta equals 3/8. In a full data simulation with the typical configuration of MPAS, you would not see that noise. But we saw it in these very specialized tests, and we decided that we would go with this weighted average in order to remove the issues associated with the formulation that didn't have that averaging. The second term we need to discretize to solve the horizontal momentum equation, where that horizontal momentum has been cast in this vector-invariant form, this equation, is associated with this, what we call the nonlinear Coriolis term, which includes not only Earth's rotation, F, but also includes the relative vorticity. So this is the full vorticity eta. And that term, eta k cross VH, k cross VH is the tangential velocity along the cell edge. We don't predict that. We don't have a prognostic equation for that tangential velocity. We have to diagnose it. The equation you see on the left here is what we use to diagnose that velocity. And the tangential velocity to the cell face, and here I'm looking at the velocity that's perpendicular to U13 here, this one here where my pointer is, the one that's pointing vertically, at least on the page here. It's a weighted sum of the velocities on the edges of the two cells that share the face. So that this green velocity here, where my pointer is computed by taking the weighted sum of all the velocities on the faces of the two cells that share the edge. The cells, the velocities that are circled in red here. That's what is used in this weighted sum. Now, to construct the full nonlinear Coriolis term here, it's done differently. We don't compute this velocity and then just multiply it by the full vorticity evaluated to the edge. Instead, we actually take a weighted sum using these weights for W times U, here are the weights here that show up in this tangential velocity reconstruction. We take those weights, and at each point where we would apply them, we multiply them by the density, and we multiply them by an average of the vorticities at the full vertical vorticities at the edge where we're doing the reconstruction and whatever edge we're using to take the velocity that's part of this summation. So it's essentially an average of the vorticities as we go along and compute the sum that's associated with our tangential velocity reconstruction. So this is a more generalized form, and what this form gives us is essentially it gives us consistent approximation of the divergence on this triangular mesh, which is the dual mesh. Now, it turns out that the vorticity lives at the vertices. Hence, having a flux divergence on this triangular mesh, on the dual of the Voronoi mesh, that's consistent with the divergence on the hexagonal, the Voronoi mesh, is very, very important because it allows for some very nice conservation properties that without which we know that the model does not work well at all. This conservation process that we've embedded in here is essential to being able to use MPAS-A. And if you look in the literature describing this, and I'll point that out at the end of the talk here, you'll see in a much greater detail how that works and why that works. So that gives us conservation properties, including we are able to conserve entropy and potential vorticity and energy to the time truncation of the integration scheme. For shallow water solvers are the basis for then the 3D hydrostatic models and finally the non-hydrostatic solver in MPAS. So that's why we use this form here and this form of the reconstruction to discretize these terms in our formulation. Now to do that, as I mentioned, the vorticity lives at the vertices. So we have to compute the vorticities at the vertices to then evaluate it at cell edges. So the formulas that I showed you on the last slide needs the vorticity at the cell edges where the velocities which we're solving for, the prognostic variables, are located, the prognostic velocities. We compute the vorticities at the vertices by using essentially the circulation theorem. We take the velocity along this edge times this edge length, plus the velocity along this edge times this edge length, and the velocity along this edge times this edge length of the dual mesh here. We compute that sum, and then we divide it by the area, and that gives us the vorticity valid at that vertex. The only term we're going to look at in the nameless.atmosphere that controls the configuration of MPAS-Atmosphere related here to the dry dynamics and the horizontal discretization is the term config_APVM_upwinding. APVM stands for Anticipated Potential Vorticity Method, and this method was developed by Sidorny in the 70s and 80s, he and colleagues. And essentially what it's doing is it's dissipating entropy. Entropy is the mean square vorticity, and it's appropriate to dissipate entropy, particularly at large scales where the flow is characterized by a downscale entropy cascade. If you don't include dissipation that affects mean squared vorticity, this affects entropy, it piles up at the small scales, at the fine wave numbers, and you get a noisy solution. So this was considered sort of an ad hoc turbulence parameterization, if you will, for models run at large scales. MPAS-Atmosphere is often run at large scales, and it makes sense to include it, and we do. The parameter here is a real number, 0.5, and that parameter controls the upwinding that's used to approximate the vorticity at the velocities located on the edges. Now, if that parameter is 0, where we're not doing any upwind approximation, what that means is it says that the average, or MPAS uses the average of the vorticities at the vertices, where it's defined as we discussed on the last slide. It uses that average to define the vorticity at the cell edge, where the velocity is located. So it's just the average of the vorticities at point A and B. That's what happens when you set config AVPM _ upwinding to 0. The default value used in MPAS is 0.5. And what happens there is that the vorticity that's computed and valid at that cell face where the velocity, the normal velocity located, is equal to the average of the vorticity at the cell centers plus an upwinding of that vorticity, which is denoted here, and that's just 0.5 times delta t times the normal velocity times the normal derivative of the vorticity valid here, plus the tangential velocity, which we diagnosed, as you've seen on the previous slide, times the derivative of the vorticity along the cell face. So this is just a first-order upwind approximation. And by using that, that will allow for this vorticity dissipation. The 0.5 is how far out in time you're integrating backwards in time to produce that upwind value. And this is essentially centered in time. So it has some goodness value there. Now, some of the MPAS meshes, particularly some of the variable resolution meshes, can have very small cell faces. There'll be a few very small ones. So if you look at the stability of this form of an upwind approximation through the vorticity in terms of stability of this as a transport scheme, because that's what this is, it's a transport scheme cast in advective form. If that cell face is small, then this term here, which is the tangential velocity times the derivative, this can have a very strong constraint on the stability of this estimate of vorticity. It can start behaving very poorly. So there are a few meshes, in particular our 15 to 3 kilometer mesh that we have in the MPAS mesh collection, where several of the cell faces are very short, and hence using 0.5 is not recommended. Typically when we're down at such a high resolution across this entire mesh, it's down to the mesoscale and even cloud scale, setting this parameter, this config AVPM upwinding to 0, makes sense. So that's the one parameter you need to be aware of. And if we find that a mesh has cell faces that are small enough that really you should turn this off, we make a note of that on the download page for those meshes. So to conclude this talk, there are 2 papers you may want to look at, and you may want to look at references within those papers that describe the MPAS mesh and the implementation of the MPAS model. The first is the main paper describing the non-hydrostatic solver, and that's Scamrock et al., available monthly weather review. A second paper in Journal of Computational Physics which is first authored by Todd Ringler, and that goes into great detail on the aspects of the discretization that I described in this, particularly the vector-invariant form of the horizontal momentum equation, and also talks about how the vector reconstruction of that tangential velocity vector along the cell faces, how that works into the vector-invariant solution of the horizontal equation of motion. The conservation properties are described and why they work. It goes into great detail. So any of you who are really interested in more details on that, how the model works, please go to those papers.